Okay, so the question was why in some of the models that we talked about do we have a direct path from the column of ones to the criterion and other times we don't. And to make that a little bit helpful, I was talking with someone, not in the class, about this topic, and it seemed to help to talk a little bit about the matrix algebra involved. So recall that I generated a little example data set, and this particular model is the analysis of variance model. Now that we talked about the fact that a model needs to have as many parameters as you have unique elements of the variance covariance matrix, or in this case, the average sums of squares and cross products matrix. Long story short, in this diagram is a statement about three means: the mean of group 1, mean of group 2, mean of group 3. And you can arrange that in your head in a couple of ways. You can say, in the ANOVA model, I just want to know what the three means are. Or alternatively, I might want to say, relative to a control group, how many points above or below the mean is that person? So two things. I mean, I made some additions to the handout because the person said, well, if you show me the matrix algebra, that makes a lot more sense. So I took the data that are involved here, and I said, well, if you're analyzing this as a path diagram, here's your y variable, and here's your x matrix for the ANOVA model. So notice we don't have a column of ones in this x matrix because we're just drawing the analysis of group 1, group 2, group 3. It's not possible for me to go back, for example, and use the old regression formula, x prime x inverse x prime y, and then say I want to be able to predict d1, d2, d3, and y, because that matrix isn't a full rank. But for the moment, if we go back to a statement I made earlier, that as long as I point from the column of ones at these variables, everything else is a variance covariance matrix downstairs. This is what the matrix looks like. And if we come down to a two-group model where I have a control group and I'm wanting to know how many points above or below that mean that particular control group is, this is what my model looks like. And you can see the column of ones is represented here, and that corresponds to this arrow when I do x prime x inverse x prime y. And for group 2, they have a 1 on this first variable, and everybody else gets a 0. And for group 3, they have a 1 on the third variable, and everybody else gets a 0 there. And you can carry that forward. I have pushed this new version to the electronic version. But if we're looking at orthogonal contrasts, this is what the matrix looks like. Well, what makes this orthogonal? Well, first of all, the mean of this vector of this variable is 0, and the mean of this variable is 0 because all the ones are balanced by minus ones. And to look at what the covariance is, I can take the product of these two numbers. Well, -1 times 0 gives me 0. 0.5 times 1 gives me 0.5, but that's balanced off by an equal number of people that have 0.5 multiplied by -1. So that's why the covariance of this variable and this variable is 0. So to come to your question, why do we have the column of ones point down here? It depends on what we want to do. In the case of this orthogonal coding, I'm interested in knowing what the grand mean is, the mean of the y variable taken over all the observations. Upstairs here, I'm interested in knowing how many points above or below the mean, of the control group these other two groups are. So it depends on what you want to know. It's kind of a long-winded way of saying that.
So can you repeat one more time why we add ones column to the matrix?
It depends on the, well, actually, all the time we're adding a column of ones. Even up here, we have a column of ones present in our model, but it's going to have to wait until the chapter where we talk about using matrix algebra to fit this full path model to talk about the math that would actually have the X matrix have that column of ones present. So in the case of the ANOVA model, I'm just looking at the parts, the arrows that go from these manifest variables to the criterion. So the column of ones is always going to be present. It's going to be, you know, I've got to tell you in another lecture how path diagram programs have the column of ones as well as these other things in here to actually recover the values that you're looking at in the diagram. You believe that?
So I think I also remember from the previous classes that we need these ones, but my question was for this when we look at the metrics here, and
Yes.
also when we look at the metrics related to orthogonal codes,
Yeah.
so we don't. So for X, I think for here there is no ones like all the way. So yes, here for example for X side, the first column is all the way ones, consistent of all the like all ones. But for the top one, the other one, the first one, we don't have this ones column.
That's true, because I'm showing you the matrix algebra for doing a regression. The matrix algebra, if you're for using X prime X inverse X prime Y, the matrix algebra for a full path diagram is going to have the column of ones in there. But we don't have the math yet to say, oh, and you know, my X matrix has a column of ones and these other codes for each of the means, because in path diagram work, it's going to go through a different set of machinery to give you not only the means of the three groups, but also the means of the predictor variables, which in this case is 1/3. So, you know, you're not seeing anywhere in the analysis these three numbers. And, you know, that's part of what you would find in the path diagram if you use software like Onyx to solve it. It'll come.
Okay.
Any other questions? I mean, I like them. It shows you're engaging with the book or engaging with. So I want to repeat something I said at the beginning of the class, that anytime you're doing a statistical model, you need to think about why you're doing that. And you are not doing it to recover truth. You are doing your statistical model to propose a conjecture that tests a theory. And that test is always going to be made against the counter arguments that a reasonable skeptic might make. You folks can use Google, and you would find that within psychology, there is a replication crisis. That is, when people do studies, often when someone tries to repeat that study, they are not able to successfully find the same conclusions, the same statistical significance of the tests involved. And part of that is a legitimate criticism of the way that we do research, that it's very hard to get null findings to be published. And as a result, only statistically significant findings get press. And all those times that someone looked at the hypothesis and didn't find it are unknown to the research community. That's known as the file drawer problem. The other problem, a second problem, is that people misunderstand the replicability of a study and its relationship to the statistical significance of that study. And the third issue is that researchers have perhaps not been assumption checking the model to see if the data actually meet the assumptions of the statistical model. So we can't do much about the first problem of the file draw problem here, other than to note that preprint services are increasingly available and researchers are able to post their findings on web hosted platforms or blogs, and as a result, maybe at least some information will get out about these null findings. The second issue, that is, failing to understand statistical significance and its implications for replication, I can handle with a short example. Say, for example, you were doing a study on, what is it called, power stances. That's one of the examples people chat about, namely that if when you're talking, you put your hands on your hips and you spread your feet apart and you look assertive when you talk, people are more likely to agree with you and to listen to what you have to say. Some people actually make a lot of money giving talks about power stances and how to improve your life and the business community. Well, say you were interested in looking at two groups and the degree to which they employed power stances. Men or women, black or white, something like that. And you did a t-test, and you found that that t-test was statistically significant at the 0.049 level. Now, if we were to say that the difference that you found was maybe actually the population difference out there, and you did the study again, how likely would you be to find that statistically significant? You can Google these types of discussions. Studies of researchers have found that there's the impression that if you have found something significant at the 0.049 level, that if you redo your study again, you should have a 95% chance of finding statistical significance. And that's not true. That if the null hypothesis, if the difference you found is in fact the true population value, when you replicate the study, you're just as likely to fall a little bit short of the mark as you are to fall a little bit farther on the mark. So a little less than half of the time, if you redo your study, would you find statistical significance. That's one thing to look at. So your p-value doesn't speak to replication, is my point. Secondly, one of the big criticisms in replication psychology these days is, well, out of the several hundred of times that you did your study that this was done, it only replicated 30% of the time. That assumption brings with it that each of the researchers doing the study did their analysis correctly, and that the pattern of statistical significance and non-statistical significance was not unduly affected by violations of the model. So let's take a look at our models here. This is a little magic trick that I used to use in lecture. I would talk to people and say, a researcher did a study and they found an X and a Y, and they found that the correlation across all 4 studies was -0.55, And the unstandardized regression weights and intercepts were identical across the 4 studies. And the p-value is less than 0.01 in all cases. Is this a great victory for science? Well, not seeing the following picture, people would say, oh yeah, this is a great replication. But this little data set, which was the object of an American statistician paper a few years ago, says, well, in the first case, yes, it kind of looks like there is a nice linear relationship, and there's some error going on here. In the second case, the researcher has, as we say, maybe left money on the table, that the relationship between X and Y is actually a curvilinear relationship. And if you would have not assumed a straight line, you could have actually come close to a perfect prediction of all of these points, in this case, considering a quadratic model. Down here, yes, I've got a nice straight line. As a matter of fact, if I just didn't have this person right here, I would have predicted the relationship between X and Y perfectly. In addition, the errors of prediction in this model, because I included this person, is a lot larger than it would have been. This particular data point, that is, a data point that causes my regression line to have a lot more errors in it than it otherwise would, is called an outlying observation, an outlier. To the extent that this observation also influences the regression line I fit to the data, that observation is said to be influential. So those are 2 words that I use very distinctly, and your advisor and your research group and your reviewers of your articles frequently don't draw that distinction. But if I'm going to get a different regression weight with the person in than with the person out, that's an influential observation. If this person increases the amount of error of prediction, I'm going to call the average amount of error of prediction, I'm going to call that person an outlier. This last example is a case of an observation that is purely influential. That is, I have everybody down here, and I have one person with a value of 19 and 12.5. If I didn't have this person in my study, and I redid the study, I probably wouldn't, if I ran the study again, I probably wouldn't have this person. And I would find that there's no variation on the X variable at all, that a regression wasn't possible. The observed value of my regression rate is entirely a function of what this one observation is doing. So the influence diagnostics that we'll talk about below here are all ways to examine the question of, is actually the relationship that I assumed up here in case 1, is that a justified hypothesis? I'm trying to talk slowly to introduce the topics. Sometimes there are questions at this point, so I'll throw it open.
I have a question. So for this 4 graphs, the one on the bottom right,
Yes.
so when we remove, so we need to check for outliers, and for the other one, to the top one, we need to find another function. But what about the one, so the other one, it is bottom left.
Yes.
So can you repeat one more time? What's the problem? Is that the function doesn't fit well, so we need to find another function, or so other than that, what can we do with this graph? What's wrong?
So I'm saying that an observation is an outlier if the errors of prediction are in the model, in the data, are a lot larger with the observation in than with the observation not in. Here's a thought. Say instead of having this unusual observation happen out here, what would happen if we would put this unusual observation right here at the mean of X?
Okay, I see. I think I understand it now. I didn't see this small dot on the top.
Oh, yeah. Sorry.
It was very, so I didn't notice that. I just saw
It's okay.
the numbers.
Right. That's
I got
fine.
it now.
That's okay. And it's also okay, you know, you don't have to have questions. You can just say, you can paraphrase and say, you know, so what you're saying is, and we'll see if, you know, sort of a counseling psychology trick, but that's fine.
Thank you.
All right. So what we're going to do is to explore regression diagnostics that you can run that will check for, is the functional form what you think it is? Is there an outlying observation, or is there an influential observation? In both these cases, this is an observation that's outlying and influential. If I had somebody here that was at the mean, well, they're going to raise the intercept a little bit, but they're not going to affect my value on the regression rate. Happily, in structural equation models, software, checking for outliers is an option. For some of the things that we'll talk about, you'll need to use SPSS or SAS or R and run a few of the programs to check the functional form relationship. Those things are not usually in the software. So let's talk about one of the ways that we might check for the functional form. And this is called low-S regression. What low-S regression does is it takes a little slice of the data that you have and calculates a very localized regression line. And then it moves over one and it does another regression, and it moves over one and does another regression. And then it smooths these things together. So inside of R or inside of SAS, you know, the low-S program will generate this kind of a program for you. Well, when this width of how large of a chunk of your data to take is called a window. So for example, if I used a window size that was all of the observations, I'm just going to recover a straight line. If I use a very small window size, I'm going to have something that has a lot of bumps and, you know, valleys and peaks that are maybe not that relevant. So inside of the software that you have, low-S regression can be used, and you can play around with the window. And sometimes people will say, well, what do I use for a window? And my answer is that it does not matter. The important thing is you explore a variety of window sizes and gain a sense for what the shape is. So in this example, low-S regression quite nicely tells us, hey, there's a quadratic function going on here. You should not be drawing straight lines. A low-S regression down here with that influential observation tells me, oh, well, you know, there's a region here where I can predict perfectly. And then kind of up here, I should be predicting something different than the straight line. So, you know, some of your bumps in a low-S regression could be due to an influential observation. And in this last case, we don't have any output because there was only one observation that was different than all the other ones. So I didn't get any data in this case because I was trying to calculate a regression where all of the X values were the same. And you know, that's basically all there is to low-S regression. If you want an example of low-S regression, one of the data sets I played with quite a bit is called the impacts data set that Ken Sure works on. And they were looking at how many drinks people consume in the last 30 days and how that predicts enhancement reasons for drinking, whether it's the belief that if I drink, the party will be better or I'll enjoy the time more. And yes, you can do a regression. You'd find a regression slope. But the lowest curve through here suggests that the action, the actual relationship between these two variables where things are happening, breaks off after 5. So really, we should not be using a straight line here. We might want to rescale this and say, if you have 5 or more drinks, I'm just going to put all these data points and put them over here. Inside of R, if you're interested, I use ggplot. That has a way of jittering these dots so you can see all the dots. Because this was a discrete Likert format or categorical response variable, if I didn't jitter them around, I would see only a single dot. There'd be all these people there. But that's an example of what a LOS looks like. More generally, a LOS curve, I mean, you could say I'm going to rescale the data set so that I can recover the regions where the association is linear. Sometimes maybe the curve that you see will suggest a parametric form. Up here, it's a quadratic curve. There are other parametric models that you can use. So, life in the time of COVID, we talk an awful lot about exponential growth in looking at the beginning of a pandemic. Combined exponential or logistic growth is appropriate when you have the whole range of the life of the pandemic. And you could use lowest regression to suggest a curve that would be a mathematical model for the relationship between the two. But my take-home message to you here is, as you are looking at your data in your project, in your thesis, in your dissertation, you're to be the expert on what's going on. And lowest regression would be the first tool that you might have to have a check on whether that relationship is linear. Comments, questions, or reinterpretations about that?
I have a question.
Yeah.
So for example, here on the y-axis, we have enhancement reasons for the ranking.
Mm-hmm.
So what would happen if we take the mean of all observations and then draw a plot that let's say we split the data into 2 groups,
Mm-hmm.
below mean and above mean, and then make a plot, 2 plots. Do you think the shape will be the same, like this line here, curved line, or do you think if its shape changes? I talk about this particular case.
So that's an interesting question. And the last chapter of the book talks about categorical dependent variables, that is, criteria that have only one of 2 values. And you could certainly say, I'm going to say above or below the mean is a dichotomous variable. Mm-hmm. There's nothing to stop you from doing a lowest regression if you have a categorical dependent variable and a continuous predictor. So you can feed those into LOS or R and mm-hmm. recover whether the relationship looks linear or not. And if you're doing a logistic equation or a probit regression, I mean, this sort of gets you into what's in the back of the book, you should expect to recover a straight line. And if it isn't, that is just as good of information about your need to transform the X variable or to adopt a different model. Another thing people sometimes do, especially in substance use, is they'll say, actually, this shape that I have going on here is evidence that I need to actually be running 2 regressions. One regression for people who are below 5 and another regression that's going to look pretty flat in this case for people above 5. So it can be done. Often in research, when you have a continuous variable, people don't like categorizing it into above and below the mean because you generally lose a lot of statistical power. Right?
Why are you losing that statistical power? Is it because you're decreasing the variance?
I'm sorry. Oh, why do they not like it categorical?
Yes.
You're decreasing precision because, maybe for the moment, let's just pretend that we have only data that went above and below 5. Well, if I take a mean, maybe some of the people here who are above the mean really kind of belong below the mean. You're losing the precision or the accuracy of the measurement. That's all there. And if you had, for example, a large sample, like in this case, there are ways to treat the data. Again, we're talking about stuff that's in the last chapter of the book that use thresholds to map what the relationship is between the little categories that you have here and the continuous variable. But yeah, if you can at all, I'm kind of in a favor of keeping the y variable as you can, unless you have some evidence that you need to transform the y variable. Now, having said that, Joy, the other thing that people will sometimes do is they'll say, well, I don't like my y variable, maybe it's skewed or something, therefore I'm going to do take the natural log of the variable. And that's also not very good, because that's assuming in lay hand-waving terms that the criterion variable, that's the actual number you have, is incorrect. What you really need to be analyzing is the number of digits in the criterion variable. So in addition, you can lose a lot by uncritically just taking a natural log. And that's why, if you had the class with me Box-Cox transformations that will tell you what should you transform, should you take a reciprocal, should you take a square root in trying to fix your y variable, are kind of good ideas. Well,
I have another question.
Yeah.
So you said, so I previously used this lowest function in R, but I want to see the functional form of the line. Is there any way to get this functional form? Like, for example, for this line, maybe it's say x squared plus something like this.
There isn't one function that gets recovered. It's a graphical function. If, however, what you're saying is the reason I want to know the mathematical form to that line is because I'm interested in identifying a cut point to run people, say, above and below that value. That gets you into something called a field called spline regression, and you're looking for a knot, K-N-O-T. And there are other programs. I can't do a deep dive on them here, but that's what office hours are for, where you can run software that will identify a cut point for you. But actually, in the case of a bivariate, it's you can trust your eyes largely, and the answer that you would get out from an empirical knot is going to be pretty close to what your eyes would tell you. As a matter of fact, that's how they often in research articles judge the success of an approach. So, lowest regression is your tool to assess functional form. In this case, it identified our quadratic curve. Residuals. Well, whenever you run a regression, you're going to get residuals, errors of prediction. And I want to take a little bit of time to chat about residuals, because often when we do run our model with and without residuals, we're kind of lazy about it and we don't think about it. And the thing that I'm trying to warn against here is that even when social scientists look at residuals, they often say, well, I went through and I looked at the residuals and I threw out all the observations that were really large residuals and I reran my model. And that's a bad idea for reasons that we'll outline here. And the short answer to spoil the story, what you want to be looking at is something called studentized deleted residuals. But let's back up and talk about residuals slowly first. So a raw residual is just the distance between a predicted value and the actual value in the data. And if you're thinking about your data graphically, you might, this is the first data set. We might also add this thing called the confidence interval for the individual predictions. You'll notice that it has this rather pleasing hourglass form, that the farther you get away from the mean of X and mean of Y, the larger the confidence interval becomes. So it might be fairly unusual to find an observation, as we did here, which falls outside the confidence interval if you're close to the mean of X, mean of Y, also known as the centroid. That's a fancy term for the joint mean. But a large residual is not at all uncommon as you move farther and farther out. And there is a reason for this. When you fit your data with a regression line, that contained a little bit of error. In other words, this regression line that you observed is not the true population regression line. It had some slop, maybe just based on your data. You had 0.22 instead of 0.20. You don't know which direction that error is, but the farther you get away from this line, in other words, you can think about this line as maybe having a slightly higher slope or a slightly lower slope, that confidence interval is going to be larger and larger. So it's quite okay to observe a residual of 3 if you're far away from the mean of X, mean of Y. And maybe it's more serious if you're right at the mean of X, mean of Y. So my point is, you can't just go through and say, I looked at the raw residuals and I threw out large residuals. As a matter of fact, that's cheating yourself a bit, because observations that are far from the mean are also those that are going to increase the power of your study. So simply going in and throwing away large residuals and going, oh, well, now I guess I don't have significance anymore, could be an artifact of the fact that you have reduced the variance of the criteria of the predictor variable by throwing out those observations. It's helpful to think about this as a scatter plot for a moment. If, for example, I threw out observations that were far away from X and only did observations here in the middle, I'd have a scatter plot that looked very close to 0. If I have the full range, I'll have, a good test of the slope. If I had only extreme groups, only extremely low observations and only extremely high observations, I would have an even larger R-square because I've thrown out the imprecision down here. So don't just do raw residuals. We need to do something called studentized residuals. And it's helpful to think about this as a scatter plot issue. The act of studentizing is going to take the confidence interval that we observe between X and Y and turn this pleasant hourglass shape into a rectangle. And the math behind it is not, terribly important to you. It does involve something called the lever that we'll talk about later. So that's kind of a spicy little detail for what goes on later. But the studentized residuals, as you look at them, a large one that's really and truly large will come out as appearing large after it's been studentized. Well, but even that is not the nicest way to check if an observation is outlying, because consider the Anscombe case number 3. All of these observations down here had errors, had residuals, but they would have had no residuals if this observation had been thrown out. So studentized deleted residuals calculate the residual that would be observed if the regression line was fit to all of the other observations. So in the case of the studentized deleted residual for this observation, I would find that I'm fitting the regression line to all of these observed dots and calculating the distance from here up to here instead of the residual from the fitted regression line up to here. So studentized deleted residuals are a little bit more accurate for that reason. And happily, studentized deleted residuals are an output that you can have in, any regression program package that you have, or in several of the structural equation software programs that you have. And for the data set number 3, I calculated the standardized residuals and the studentized deleted residuals, just so you can see how those values change. And you can see, well, when I studentize delete them, I pretty readily flag that one observation as being really large.